Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Planet X Causes the Sun to be Darkened. Now, when Jesus said in Matthew 24 verse 29, immediately after the tribulation of those days shall the sun be darkened, he meant just that, because the sun is now being darkened. In other words, the sun is literally going dark. In this article, I will detail how I discovered that the sun does go dark. Now, when I started investigating the Planet X phenomenon, I did so because I saw pink-colored clouds in the sky, and I knew that it was impossible that such a color could be observed in the sky unless there was a source of the light other than the sun emitting this color of light. What I discovered was beyond anything that I could imagine would even be possible. Observations in the form of images showing the objects in the sun's corona do not lie. These objects are real, and the implications are astounding, as they change just about everything I was taught. What I learned has led me to discover what causes gravity, a question that I was often asked by my students when I was still lecturing at the University of the Witwatersrand in South Africa. Gravity comes from the photon or light, as does everything else in the universe, and the strength of the gravitational interaction is determined by light or photon energy inside the particles of an object. And you may look at article 190 entitled The God Particle Turning Light into Matter, and article 210 entitled Stellar Core Gravity, tidal, and G is not constant. And here we see the latest of Scott Sion's discoveries, and that is another one of these stellar cores in the sun's corona. And you can clearly see that it's a spherical object in the sun's corona, and the typical connection that they make with the sun, through which they draw energy from the sun, it's a root-like connection in a form of a vortex from which they draw matter from the sun. This is how they acquire their atmosphere, from which they then start emitting light. And so here they are. This is not the only one. There are many, many such images showing these objects in the sun's corona. But on the way to discovering the truth about gravity, I first discovered that the sun was going dark at certain times. The fact that it was going dark could be seen in the images obtained by the STO satellite during the so-called STO eclipse season, which is supposed to occur twice per year. From the time I saw these images showing the sun going dark, I knew that only the sun actually going dark could actually produce these types of images. These could not have been produced by an eclipse, and therefore the eclipse has to be a cover story. The realization that the sun was capable of going dark was a huge step in my understanding of what was going on in the solar system and of how the universe really works. For one thing, it means that just about all current accepted astrophysics theory, which is based on stars being powered by thermonuclear reactions and on gravitational collapse, is completely wrong. This is because there cannot be any thermonuclear reactions occurring in the sun, as if there were, there would be light continuously coming from inside the sun, and it would be impossible for the sun to go dark. Thus, the understanding that the sun is going dark is of extreme importance in the understanding of how the universe really works. I have written about this many times, but some people still find the arguments difficult to understand. So in this article, I'm going to attempt to explain it more clearly. And these are images from the STO satellite from August 16, 2017. This was the first day of the eclipse season in August. It's the second one of the year of 2017. And these images are in 21.1 nanometers or 211 angstroms. They are between 703 and 714, and they show the sun getting progressively darker. The sun does not go completely dark in this wavelength on the first day, but it takes longer as well for it to go dark on this day than on other days. So this is the perfect day to study what happens to the sun as it is going dark. But completed structures are seen at the edge of the dark/light interface. As you can see, completed structures everywhere. The Earth does not seem to be partially covering anything. We never see something that appears to be half of a structure. We only see completed, perfectly edged structures. This and the shrinking corona shows that the sun is not being eclipsed, but is actually going dark. And you can see that the corona is shrinking. Say here, you compare what the corona looks like here with what it looks like there. You can see how far from the face of the sun it seems to be there. It's not nearly as far here. So it has shrunk. It shrinks even more in the next image. So clearly the corona is shrinking. And this shows that the sun has to be going dark. Now, SDO's orbit and the Earth are drawn to scale here. SDO's orbit is a 24-hour orbit because it's a geosynchronous satellite with a 28-degree orbital inclination. So the Earth can only block the satellite's view of the sun twice per year. And this is illustrated in this image. As the Earth moves around the sun, there are only two positions where the satellite goes behind the Earth and its view of the sun would be blocked. So at these two positions, you can see when it is behind the Earth, the satellite is either below, like on this side, or above the Earth. So its view is not blocked. But when the Earth is in this position, then the satellite does go behind the Earth there and goes behind the Earth here. So on this side, it's red because it's facing us. On that side, it's orange because it will be behind the Earth. So we wouldn't see it. We wouldn't see it from this perspective. Then, using the fact that the Earth's radius is 6,371 kilometers and the Sun's radius is 696,300 kilometers, and the distance between the Earth and the Sun is 152 million kilometers, we can calculate the Sun's angular width, which is the diameter of the Sun, so twice its radius, which is given by that, divided by the distance between the Sun and the Earth, given by that. And then that would give it to us in radians. We can then convert to degrees. It's 0.52 degrees. And the Earth's angular width, as viewed from SDO's position, is then the diameter of the Earth, twice its radius, divided by the orbital distance the satellite is at. So that's the radius of the Earth plus its orbital altitude, and that's 42,100 kilometers. It is known for a geosynchronous satellite. It turns out that the Earth's angular width is then 17.3 degrees, which means that the Earth's angular width is 33 times larger than the Sun. So we can then draw the Earth's size in comparison with the Sun's from SDO's perspective. And this is what we would obtain. You see how tiny the Sun seems to be with respect to the Earth. So if the Earth then is covering the Sun, this is what it would look like. As you can see, there's a slight bulge, but it is so slight that it's almost as if we have a perfect triangle with a straight line here. And this means that the Earth's curvature compared with the Sun's is almost flat. A flat curvature means infinite curvature or infinite radius of curvature. So we can use a triangle to represent the Earth. And this is what we're going to do below. Now, one of the arguments that a colleague of mine who is an astronomer gave me in order to discourage my stand on the SDO eclipse season was that part of the Sun can be viewed through the Earth's atmosphere. However, the Earth's atmosphere absorbs all extreme ultraviolet and X-ray wavelengths coming from the Sun. SDO detects several extreme ultraviolet, one X-ray, and one visible light wavelength. So only one wavelength, the visible light one, can be affected by the satellite viewing the Sun through the atmosphere. This is why satellite is used to view the sun in extreme UV in the first place. These cannot be viewed from within the atmosphere. And the sun cannot be viewed in extreme ultraviolet from within the atmosphere because the atmosphere absorbs extreme ultraviolet. In addition, even though up to a third of the sun could technically be viewed through the Earth's atmosphere if the atmosphere was transparent to extreme ultraviolet, it is obvious that features which are bright within that 1/3 remain equally bright in subsequent images until that section goes dark. And we can see it here. You can see the brightest feature on the sun remains just as bright as the sun seems to go dark. And there's up to a third. So a third would be here, somewhere here, but definitely would be within that 1/3 here, but it's just as bright. There's another part here that's quite bright and also remains bright, and it's within that 1/3. There's even a part here that remains just as bright in all the images. So clearly the sun is not being viewed through the Earth's atmosphere. Now, so let's go back. Let's go back here. So obviously, there is no way that we are seeing and that some of what we're seeing can be caused by the satellite viewing the sun through the atmosphere. Now, we have an image here where half of the sun seems to be dark and half of it is still emitting light. Now, if this was due to an eclipse, then we would have to have the Earth covering the part that is dark. So the question then is, where would the Earth is? And the Earth here is represented by the blue circle. The blue triangle. So the blue triangle represents the Earth. We know that the Earth actually has a very gentle curvature, but we can approximate it with a triangle because it's almost flat. Now, where would we position the Earth? Would we position here or there? Well, if we position it here, which I think is more likely, because then we would be able to see the corona right up to the point where it's flush with the face of the sun. And over here, it would cover up this part that is going dark, but then we shouldn't be able to see this part of the corona that would be covered. So this is the more likely position to place the Earth. Right. Now, if we then take that same image where we've determined where to position the Earth and compare it with an image of the sun from 4 minutes before, if this was produced by an eclipse, we'd have to have the Earth covering the part of the sun that is visible in this image, but is now gone in this image because it's covered. So we can compare what's visible of the sun here with what is produced in this image. As you can see, so there's the edge of the Earth. Let's look at the corona. Well, the corona goes up to there, but we don't see it doing the same thing here. How can the Earth cover produce this darkness here in the corona? And it doesn't look like it's being covered at all because it's edged in darker purple. So that shows that this is actually the edge of the corona. And it therefore shows that the corona has shrunk from where it was here to where it is there. The same thing happens on that side. So we see that the corona has shrunk, and this cannot be explained by an eclipse. An eclipse can only cover part of the sun. It cannot cause the corona to shrink. So the Earth, in addition, we have this darkness here. which should not be there. This part of the sun should still be visible. And even though this is an approximation of the curvature of the Earth, the actual curvature, which is shown here, is so gentle, there is no way that it can produce that curved and an interface between darkness and light. Now, and how can cellular-like parts of the sun remain visible below the edge of the darkness? So you can see little cellular-like parts of the sun visible below that edge. If this was actually the edge of the Earth, so the Earth was covering that part there, how would we then be able to see these little spots that remained on? Is the Earth supposed to be covering them? Are we looking at them through the Earth? As we know, there is no way that any part of the sun is being seen through the curvature, through the atmosphere. Already showed that. So it's impossible that these pieces can actually still be seen. As you can see, this thing here is just as bright as it seems to be there. No loss in brightness. For that little bright spot, it still is white. How is this even possible? Now the sun does not seem to have been covered by the Earth at all. There's no sign that the Earth is here in front of the sun at all. And it is as if a coronal hole is spreading across the face of the sun. And this is the new edge of the coronal hole. This clearly indicates that the sun is going dark, and it is not going dark due to an eclipse, but rather due to loss of light emission. And in addition, as you can see, this coronal hole seems to have grown. How is, if you compare the size of this coronal hole and its edge, you can see the edge of the coronal hole here. That edge should still be here, but it's not. It's grown. Even a coronal hole that's way above where light emission is still going on has grown. This shows that the sun is decreasing in light emission. It is not being eclipsed. Now, even with the Earth positioned further up, okay, it's still obvious that the corona has shrunk. If we compare what the corona looks like above the cylinder here with what it looks like there, we can see it has shrunk. We can see it's shrunk. And furthermore, there's no way that the Earth is there, because then we wouldn't be able to see the edge of the corona here so clearly. The Earth cannot be in this position, therefore. So this shows that the sun is progressively losing light emission. This cannot be due to an eclipse. This loss of light emission occurs at all wavelengths detected by the SDO satellite, as shown here. And these images are from August 18th, 2017. So it's not the first day of the eclipse season anymore. And on this day, the sun does go dark completely. The last one is the visible light, and the visible light images are only available only change once per hour. So the new frame is available every hour on the hour. And so we see what the sun looks like at 7 o'clock, and we see what it looks like at 6, what it looks like at 7, what it looks like at 8. This one is from 7, whilst all these images are from 6:52. But by 7 o'clock, the sun had gone completely dark in visible light, indicating that every wavelength, that the sun loses light emission in every wavelength, including visible light. Now, this also shows that the sun loses light emission at different rates for the different wavelengths. As you can see different portions of the sun. This is the X-ray one, and we can see about 2/3 of the sun. This is close to a half, about a half, a little less than a half, a little less than a half. more than a half, much more than a half, but at least more than 2/3, nearly 2/3. Nearly the whole sun is still visible. They all from 6:52. They only differ by a few seconds. And this one is 6:52:38. This one is 6:52:29. So this one is actually later than that, but you can see less of the sun here than that one. It cannot change by much in just a few seconds anyway. But just from that, we can see that the sun goes dark at different rates for the different wavelengths, and it goes dark in all wavelengths, including visible light. In addition, we actually, from the curvature here, which you can see bulges outwards away from the blue line, for the Earth to be able to produce a curvature like that on the sun, the Earth would have to have a negative curvature. So instead of the spherical curvature, the positive curvature that all spherical objects have, the Earth would have to have an indentation in it in order to produce that type of shape on the sun. This is clearly impossible, and again shows that this cannot be caused by an eclipse. It is therefore impossible for the SDO images produced during the SDO eclipse season to be due to an eclipse. These images can only be produced if the sun is actually going dark at this time. But how would the SDO satellite not actually observe a real eclipse twice a year as a result of its orbit, causing it to be behind the Earth? I think it is likely that there are at least 2 SDO satellites up there. And when the sun is being eclipsed for one, the other is still able to provide images of the sun. So what causes the sun to lose light emission? The sun produces light as a result of an electric potential across its atmosphere. But since the stellar cores, which are actually brown and black dwarfs, as I have shown in recent articles, and these belong to the system which I've called the Planet X system, and these objects absorb electrons and drain the sun of energy. They are therefore able to cause a drop in the sun's electric potential when they closely approach the sun. This also shows that the sun's surface cannot be any hotter than 750 Kelvin or 900 Fahrenheit. And you may look at Article 195 entitled Stellar Cores in the Dying Sun and Article 232 entitled The Sun Can Go Dark, the Implications. Now, the SDO satellite was officially launched on February 11, 2010, and the SDO eclipse season occurs in February or March and in August versus September. August, September. But in 2010, there was no eclipse season in March. So the first eclipse season was in September of 2010. Images from this eclipse season are seen here in 335 angstrom, so extreme ultraviolet again. And here we can see the sun going dark. I don't think this is the first day of the eclipse because the sun goes completely dark on that day. And as you can see, so it's getting progressively darker and then light emission resuming. And we can see the corona shrinking as well, like before, even though the corona looks smaller in this wavelength. But we can clearly see that the corona shrinks in several of these images. You can see even here looks smaller than it does there. So it's clearly shrinking already. We can see it looks smaller here than there. So the same thing occurs that occurred in 2017. Now these images are between 6:40 and 7:07 UTC. The eclipse usually lasts at least 30 minutes, sometimes up to 69 minutes. And this image is from 7:07, and that image is repeated here. This image is from 7:08, and the difference in the two images is astounding, because as you can see how much brighter the sun seems to be in just 1 minute. And there is no way the Earth would have been down here by then, somewhere down here. Okay, so it would have been just here. We can see it actually here somewhere. And it would have been just maybe here in order for us, if this was an eclipse. We know it's not an eclipse. But how does the sun, with the Earth not being anywhere near, it suddenly becomes so much brighter in 1 minute? And look how much the corona has grown from 1 minute to the next all around. On the other side of the sun, as well as this side of the sun, the corona has grown dramatically. The sun has become so much lighter in just 1 minute. Notice this coronal hole that is visible here on the left side of the sun. Look, it seems to have shrunk in size. So the size of the coronal holes has to do with the light emission as well. And obviously the coronal holes grow in size as the sun loses light emission, and they decrease in size when the sun regains light emission, obviously because the object that caused the sun's electric potential, which drives its light emission, has moved away from the sun. And when it moves away, the sun's potential comes back and it regains full light emission. Then at least it did. I didn't see this ever happening this clearly in subsequent years. This only seems to have occurred in 2010, but the dramatic difference is amazing. So in conclusion, the sun can and does go dark. The fact that the sun's corona shrinks back as darkness progresses across the face of the sun provides irrefutable evidence that the STO eclipse season images are not due to an eclipse, but actually show the sun going dark. This irrefutable observation makes all the current accepted theories about how the sun operates and how stars form, since they are all based on gravitational collapse, completely wrong. It took the invasion of the Planet X system of our solar system to show us that everything we have been led to believe about the universe is wrong. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.